All right, so today we're going to be going over Fibonacci and Jordanus to Nemore, and we're going to be specifically talking about kind of how they brought algebra over to Europe from the Hindu-Arabic system. So, first off, we're going to talk about Fibonacci. His actual name was Leonardo of Pisa, and he was born there in 1170, there being Pisa. And during this time, Pisa was under their own control, and they were known as the Republic of Pisa. This wasn't very common. They weren't usually under their own control, they were usually under control of somebody else. And so, due to this, they were in a war with southern France during his youth, and it was over conflicts in the Rhone River with merchants, as merchants wanted to use the Rhone River, but France wasn't letting them, so there was a war going on. Fortunately, it ended in 1175 when Leonardo was simply just 5 years old. Although there were others, one of them included the Venetian rule and the Adriatic Sea. That actually occurred twice. Same reason, it was just merchants trying to get in there. Another one was in Florence in 1220, and there was another one in Tuscany in 1240. And actually, in result of that war, Pisa was actually excommunicated for a few years from Italy. And as we're going to see throughout this presentation, a lot of Leonardo's works was actually based off of Al-Khwarizmi and a lot of the algebra that he had done, and kind of like the way he solved equations and such. He was a big influence for Leonardo. And so, what did he do? Well, his most famous piece was Liber Abyssine, and it was the Book of Calculation, and in which he introduced the Western world to a lot of the Eastern Hindu-Arabic mathematics. And it was also said to be the reason a lot of Europe stopped using Roman numerals. They actually went over to the 0 through 9 system that we use today, which we can credit to the Hindu-Arabic way of doing math. And so you may have also heard of the Fibonacci sequence, the one, 1, 1, 2, 3, 5, 8, 13, blah, blah, blah. It's much more number theory than it is algebra, so we're not going to focus too much on it, though we had seen in the homework before, kind of the golden ratio here, where you have a rectangle, you can cut it up into a square and keep doing it, and you get that spiral. That's actually a limit in which you divide the Fibonacci sequence, which can lead you to 1.608. You can see, 2 divided by 1 is 2, and you do 3 over 2 is 1.5, and you're going to slowly just get closer and closer to 1.6, kind of bouncing back and forth. It's kind of cool because these numbers kind of appear everywhere in nature. Pine cones follow the spiral, and flowers actually have petals in numbers that follow the Fibonacci sequence. Some are going to have 3, 5, 8, 13. It's kind of everywhere. And then he also wrote Liber Quadratorum, and it was considered a masterpiece of number theory. So again, we're not going to look too much of it. We're much more focused on the algebra that Fibonacci had brought over. So we're not going to look too much of that. And so more on this piece. It was written in 1202 and was heavily inspired by Al-Khwarizmi, as we had said. And he used a lot of the Hindu-Arabic algebra to introduce new problems to Europe. They weren't so much used to it. They were using Roman numerals. They weren't very much to algebra. They just kind of did their basic mathematics and kind of solved their problems like that. And the piece immediately begins by introducing the Hindu-Arabic numeration system, which is just 1 through 9, the same we use today. But he actually included 0 as an extra. It wasn't so much of these numbers. It was much more of a placeholder. You can see down here in the actual piece itself, you can see 1 through 9 here. And then you can see 0 is kind of by itself down here, just as an extra piece. So that's kind of interesting. And the problems in the first few sections are aimed at merchants and involve a lot of addition, subtraction, and kind of how to use the new number system. He wanted to be much more of a powerful tool for merchants than anything else. He wanted Pisa to strive, and he wanted these people to be able to do advanced algebra in a way that would only, benefit their trade. And the infamous rabbit problem is also in this piece, which led to the Fibonacci sequences earlier. He actually questioned how many times the rabbits could reproduce given the perfect circumstances over a year. And you can see you start with 2 rabbits, you're going to get 3 when they reproduce, 2 make 1. And then you're going to get 3 to 5, and then 5 to 8, and so on. And it comes to be like in the millions or something like that after a year. And so, quick summary of the sections that are actually in this piece. It's a really, really huge drawn out piece. I think it's like somewhere in the 300, and then it gets 600 pages whenever it's translated over to English. And so, like I said, it begins by introducing the number system 0 through 9. Section 2 included a lot of the problems of commerce that we had talked about for merchants. And it also included a lot of those basic binary options, kind of because they were just kind of ingrained in those problems, a lot of multiplication, addition, subtraction, that kind of stuff. Section 3 included a lot of the more theoretical based math, not so much of the application, kind of like the rabbit problem that we had seen. Perfect numbers, the Chinese remainder theorem, and even some of the negative numbers that don't really apply so much to application. And it was much more just like theory based. We're actually going to see some of those. And then section 4 deals a lot with square roots and irrational approximations. Again, very much just related to the Hindu Arabic style of doing mathematics. And section 5 included a lot of geometric proofs, and it kind of included a lot of Euclidean geometry. Again, we're not going to look too much of it. It wasn't very significant. It was very much just kind of translating him over to Western Europe. So, an example problem, a lot of his way of solving problems were very much similar to ours, and they were just kind of different notation. Like, for example, if you wanted to take 83 divided by 5 and 2/3, you'd multiply the 5 by the 3, and then you'd add 2 to get 17 over 3. You'd multiply the 83 by 3 to get a common denominator, and then you divide 83 by 17 to get your answer. And that's actually exactly how he did it. He did it just like that. It was very different from Hindu Arabic. It was much more simple and straight to the point. And he did the same thing for adding fractions. It was that common denominator idea. The notation we see below, actually the 162 over bar 2910, and then the one after it is the same as placing the one before it for us. And then having 162 over 2910 is going to be equal to 1 over 2 times 9 times 10 plus 6 over 90 plus 2 times over 10. And obviously you're the one in front of it because like he just had it over to the right, whereas we have it to the left in whole fractions. So one of the most famous problems he has in kind of this section of basic binary operations is going to be a man buys 30 live birds that includes partridges, pigeons, and sparrows for 30 dinars, which is kind of how it's just the currency they had. It's kind of like our dollar. A partridge costs 3, pigeon costs 2, and then 2 sparrows cost 1. So i.e., the sparrow costs half. And then so we're going to ask how many birds of each kind do we buy? And this problem is very much kind of how we would see in an elementary algebra book today, seen in middle school or early high school, when that we would set up equations for solve the set of equations, kind of like how you have 5 nickels and 3 dimes, how many packs of gums can you buy? So he actually did it very different. He did it in a very much more logic and workaround base. So he noticed he could buy 5 birds for 5 coins by buying 4 sparrows and 1 partridge. All right, so you get 5 birds for 5 coins. Same goes for 2 sparrows and 1 pigeon for 3 coins. So there you get 3 birds for 3 coins. So you're going to multiply the first set, which is going to be these up here, by 3 to get 15 coins. So for that, you'll get 12 sparrows and 3 partridges. And then you're going to multiply the second bit, the 2 sparrows, 1 pigeon, and 3 coins by 5 to also get 15 coins there. And you're also going to get 10 sparrows and 5 pigeons. And then you can just add the 2 up to get 30 coins, and you have a solution there. So that way you get 22 sparrows, 5 pigeons, and 3 partridges, and it works. So a lot of his solutions, kind of like how we see here, it's much more like workaround. It's not so much setting up an equation, setting for these unknowns. It's much more we're going to use logic and kind of this workaround basis in that we can make it much more simpler than having to, solve for an equation. It's as simple as we can just set these up to get 2 sets of 15, add them together, and there you go. Some of the examples of the merchant problems is also something I kind of wanted to look at because it was such a big basis for the book. It was kind of the whole reason he had written it. And so an example in chapter 8 is going to be if 2 pounds of barley costs 5 soldi, how much would 7 pounds cost? Just proportions, very basic. Chapter 10 kind of goes on to be 3 men made a company in which the first man put 17, second 29, and third 42 pounds. Profit was 100 pounds, right? So that's going to be basic addition. And then there becomes a recurring theme of mathematics. It very much deals with the currency idea. Like I had said, he wanted to be a much more power tool for merchants instead of just kind of like the basic man for theory and application. And so then we get to chapter 12, and it was a lot of these tree problems, kind of like how we'd see with the rabbits. It's very just like starts off at one single point and kind of infinitely grows. And essentially you're kind of doing ax equals b. Obviously he didn't write that. They didn't have that lettering system. And you just kind of solve for these determinate equations. Also, he had actually called the kind of basic unit thing in his piece. We had seen thing, mile, and cube from Al Khwarizmi, and it was very much a reference to those early Hindu Arabic mathematical systems. And finally, he had actually used an old Egyptian method called false position, where he would kind of just guess. And there was a reason for the guess, but it was very much just, I know this answer is wrong, but I'm going to guess anyway, and we're going to see where it takes me. I'll make adjustments throughout the way, and we'll kind of get to the right answer from there. And so I kind of wanted to look at the problem with that. So one of those problems is going to be the problem of the lion in the pit. So we're going to start off with a lion is in a 50-foot deep pit, and he can climb out a seventh of a foot a day, but he also falls 1/9 of a foot each night. And we're trying to solve how long it's going to take in days for the lion to get out. So he just immediately guessed 63, and he did this because 63 is divisible by both 7 and 9. So that way, in 63 days, the lion's going to climb up 9 feet and fall 7. So there you have a net of 2 feet. So then you can take 63 times 25 to get 50, and you'll get 1575 days to climb the full 50 feet. And while this is a really solid way to do this problem, it was only wrong by 3 days. So when you're looking at like a 5-year span of 1,500 days, it's really impressive to get off by only 3 days when you're just completely starting off with a guess. So while it was really prevalent in this piece, the later chapters actually use a much more direct method in which an equation is set up and solved for some unknown, in which he'd credited that to the Arabs. And it worked much better when you started to use systems of indeterminate equations and determinate equations with, like, since there's no straight answer there, it's going to be much more efficient instead of trying to use logic to solve those, to use the system that we kind of use today of solving for a set of equations. So that should kind of do it for Fibonacci there. It was much more just taking the elementary idea of algebra and bringing it over to Western Europe and trying to get them to stray away from the Roman numerals, and instead we're going to start using this number system that makes the merchants' jobs so much easier. So a little bit after that, we have Jordanus of Nemore. He was born in 1225, 15 years after the death of Fibonacci. So Fibonacci had become a pretty prevalent name in the society. He was born in Borgentreich, Germany, although his name points very much to him being from Italy. And that kind of stems from the fact that not a lot of people know much about this guy. There's not a lot of known of his private life besides his work and his teachings at University of Toulouse. Some people thought he taught at University of Paris. Turns out that could have been a guy by the name of Jordanus de Saxonia, and we're not even still sure to this day if it's the same person or not. So it's really hard to gauge the context of the history, considering that Jordanus of Nemore is very much of a mystery. All we really know is that he had a lot of works that brought a lot of complex algebra into Western Europe, and a lot of it was influenced by Euclid. As you could see, a lot of it was much more axiomatic than these problems with numbers. It wasn't so much numerical; it was more theoretical, and kind of you can apply this to any set of numbers that you want. So, what did he do? The main thing he's known for are these 6 pieces, all dealing with mathematics. First one was a practical use of Arabic integers. Second one was practical use for Arabic fractions. And then after that, he had gone to the much more theoretical side. And the next he had devoted to European geometry and stereographic projection geometry. So you can see those 2 pieces are very, influenced by Euclid. And then the last one, it was the first advanced algebra text since Diophantus. And so we're going to look a lot at that book since it was the most prevalent for algebra. And he's credited with being among the first to start using letters. He wasn't the exact first, but he was one of the very big names in getting it started and getting the very basic use of using letters for your unknowns instead of like symbols and such. And a lot of some of the other pieces he had worked on were very like ratios and proportions, but it just kind of stretched out of Euclid's work, and it wasn't very much worth mentioning. So talking about that piece, it included 2 texts, one of which had 95 propositions and the other one had 115 propositions, all of which were problems to be solved. So like we had said, it was very based off of Euclid, whereas propositions are all problems that you solve instead of just like ideas, so you can apply them to kind of anywhere. And a lot of it was work based off of early Arabic resources. And as I had said before, it is the very first text to bring very advanced algebra to Western Europe, kind of straying off of Fibonacci, who had brought a lot of the more basic algebra. And a lot of his work was also inspired by Francois Viette, in that his method included formulating an equation and finding the solution by transforming his equation into a solution by introducing unknown numbers into the equation. And if that sounded long out and stretched, it was much. It just resembles exactly what we do today. We have an equation with an unknown variable inside of it, x, and then we just manipulate the equation to solve for x, and then we plug in our numbers and we have our unknown solution. It's kind of what you see in upper middle school, lower high school algebra textbooks. So the treatise contained a lot of solved problems, and it shed a light on how much some of the advanced mathematics that Arabic had really started to develop in that time. So the first example problem I wanted to look at is if a given number is separated into two parts such that the product of the parts is known, then each of the parts can be found, right? So we're going to let the given number a be separated into x and y, so that the product of x and y is b. So xy is going to be b here. Moreover, let the square of the sum of x and y be e, and the quadruple of b be f. We very much see that here in this equation. And then you subtract from this e to get g, which will then be the square of the difference of x and y. You're going to take the square root of g, call it f. Then h is the difference of x and y. Since h is known, then x and y can be found. And it makes a lot more sense than when you plug a number into it. So we're going to go ahead and just use 10. And we're going to say that the two products make the product 21. So we're going to first quadruple 21 and then subtract it from the square of 10, which is going to be 100. We're going to get 100 minus 84 is going to be 16. We're going to take the square root of 16 to get 4. And then we know that that number there is going to be the difference of our two parts. So subtracting 4 from 10, we're going to get 6. Have that, we're going to get 3, which is going to be the lesser part, plus 4, which we know is our difference. We're going to get 7. And as we know, 3 plus 7 is 10. 3 times 7 is 21. So we have our solution there. And a lot of that is very much based off of this equation right here. He kind of knew this fact here and he used it to his advantage to formulate this equation. But it's much more worth noting that you can tell it's a lot of it is very based off of algorithmy. We see separating this idea of 10 into into two parts, and then squaring and subtracting some of the parts of them in the product. And you can immediately tell that it resembles Al-Khwarizmi's method of solving a square problem. So next, I wanted to look at another example problem. And so we're going to say if a given number is divided into two parts whose difference is given, then each of the parts can be determined. So how he had said this was, namely, the lesser part and the difference make the greater. Thus, the lesser part with itself and the difference make the whole. Subtract, therefore, the greater from the whole, and there will remain double the lesser given number. When divided by 2, the lesser part will be determined, and therefore also the greater part. And so, for example, we're going to use 10 again. Let 10 be divided into two parts, in which the difference is 2, right? And then his proposition pretty much says that when you have that sentence there, you immediately know that which your two parts are going to be. So you take 10 minus 2, you're going to get 8. Take the half of that, you're going to be 4. And that's the lesser part, and you know the difference is 2, so you're going to get 6. And what you know, 4 plus 6 is going to be 10. And if we were to take this into a much more like modern standpoint, you can see that this kind of comes out to be x plus y is a and x minus y is b. You can manipulate it and use substitution, which is really impressive that he had known that back then, that you can do that. And that we use it very often today in our algebra careers to be y is going to be 1/2 a minus b, and x is going to be a minus y. So that should do it for Jordanus and Fibonacci, and thank you.